Hello, good morning, everyone. Today we will continue from where we stopped last week, okay, on the time response. All right. Okay, so now just recap at where we have stopped previously. So last week we are trying to study about the time response. Okay, how the systems react or output. Okay, when they are subjected to different kind of models. Okay, and obviously in this case we are talking about a second order transfer functions system. Okay, with four types of response. We have over damped, under damped, all right, critically damped, okay, and so on. And after that, we are mentioning, we are evaluating the performance of our systems where we use the time rise, okay, peak time, and also the percent overshoot, okay, as well as the settling time. So as we stop there, okay, so this is the continuations of where we stop, right? So as we can see, we also want to know the performance of the second order's time response, okay, by evaluating the settling time, how long it takes to settle. Sorry. Hello. Yeah. Yeah. Ada. Okay. Sekarang nomor 10. Nomor 10 Sorry for the interrupt. Right. So we will continue that the evaluations of the time response actually can be represented by these equations, okay, that we have seen previously, okay. So because of that, okay, and by the definitions of the settling time, okay, we would define that the system is settled or at the steady state when it stay within a range of plus minus 2% away from the final value, okay, or the steady state value. So in that case, that would corresponding to this final term, okay, this part of the term, okay, because one is the final value, okay, minus this is the oscillation part, right? And because of that, this represent the fluctuations of the system, and we set this sections, okay, to be equals to 0.02, okay, and from there we can actually rearrange and we obtain the settling time equals to minus ln 0.02, okay, this is the value, okay, multiplied by the square root of 1 minus damping ratio square, okay, divided by damping ratio omega n, okay, the natural frequency. And from here we note that this settling time actually change according to two parameters, the damping ratio and the natural frequency, right? And if we further look at the numerator sections, okay, the parts at the top, right? So you will see that this sections actually depends mainly only on the damping ratio, right? So if we varies the damping ratio from 0 to 0.9, actually this numerator's value just change maybe from 3.91 to 4.74, okay. So you can try to change this, okay. So you can calculate exact value of this settling time, but to ease us, okay, to make our life easier, then actually we found that this is around 4, okay. So we would make a quick estimation or an approximations, which is we assume this value as 4, okay. We can approximate by using this settling time equals to 4 divided by the damping ratio multiplied by the natural frequency, right? Then we can also evaluate the rise time, right? And this rise times basically just depends on the time for it to reach 90% of the final value, okay, from 10%, okay. So in this case, because of the complexity, the best way is just plot the graph and find where is the 10% and the 90%, okay. Then we find the rise time from there, okay. That is the more straightforward, right? So here is an examples where you can try it on your own, okay. Just the concept is very straightforward, okay. If we are given a second order transfer functions, right, so you can exactly get the peak time, the overshoot percentage, and the settling time, okay, as shown, right. So you just apply the equations accordingly, right? Next, this is more important on the design later stage, okay, is how the peak time, the overshoot percent, and the settling time actually change, okay, or related to the locations of the pole positions, okay. So remember, we have we can obtain the pole from the transfer function itself, right? So this pole, when we draw on the S-plane itself, okay, you would actually see the positions, and if we can visually shift, okay, then we can actually control the performance of our second order system, right? So here we can see that by this Pythagoras theorem, right? So the radial distance, actually controlling the natural frequency, or detect by the natural frequency, right? So this natural frequency represent the radial distance, okay, from the origin, okay, to the pole. Then from there onwards, we can also relate that the angle, this theta, cos theta, is actually related to the damping ratio, right? So by doing this, now you can see the relationship between the natural frequency and the damping ratio, and from there onwards, okay, we would want to actually visualize, okay, how the pole change and how the system will react, okay, and from there onwards we can do our own design in the later stage, okay, that we will cover. But this is the fundamentals of it, okay, where we will look at the S-plane, okay, where is the locations of the pole, right? So obviously, again, if we want, when we know all these things, okay, then the peak time we can always control by the equations, right? And the settling time also we can get, okay, and this corresponding to this, right? Okay, so here is the basic ideas behind it, okay, the relationship between the performance, okay, the time, peak time, the setting time, okay, related to the natural frequency and the natural frequency, okay, of the damped part, right, the imaginary part, as well as the real part, okay. We just break them into two sections, right? So it's either the imaginary part of the pool or the real part of the pool, right? Then also finally we can also see this relationship between the damping ratio and the theta, okay. And because of this theta, right, so now you can see that since the percent overshoot is only a functions of the damping ratio, right, then therefore the distance, okay, or the radial line are a constant, okay, related to the percent overshoot, right? So this is where we would apply, okay, this concept, okay, to be easier for you to visualize, okay. So we will just go directly to this visual part, right? So as we can see from these pole positions, point 1, 2, and 3, okay, the pole 1, 2, 3, all right. So whether it's at the upper part or the lower part of the S-plane. So if we can move these pull positions, okay, from point 1, 2 and 3, okay, vertically, what would it affect, okay, how it would affect the performance is that when this shifted up, okay, we are actually maintaining the real part, okay, the real value is still remain the same, only the imaginary value differs, okay, and because of that the frequency increase, okay, due to the shifted positions vertically, okay, but the envelope of this damped envelope is remain the same. So you can see that the envelope is remain the same, but the frequency increase from 1 to 3 when we shift these positions, right? Then also because of that, okay, as the overshoot increase, then the rise time also decrease, right? So this is the relationship when we shift the pull, okay, from the lower part to the upper part, right? Then we also see how if we shift these pull positions, okay, from the right hand side to the left hand side, right, then we can also see that this value of, or I would say the real value now increase, okay, in the negative directions, right? So when this value increase, what happens is that, remember, vertically we are controlling the frequency, so because now the imaginary part remain the same, the frequency remain the same, okay, what happens is that when we shift it to the right or to the left, it will now affect the what we call the peak time, okay, or the peak value, right? So we can see that the percent overshoot actually change, right, because of this, okay, so because of the shift, okay, so you can see that the peak change, right, whereas the frequency remain the same. So we can conclude that as the pull move to the left, okay, the response actually damp out faster, right, and because of that also the frequency, however the frequency actually remain the same, okay, due to the maintain of the imaginary value, right? Then the last changes that we can see is that when we set from when we shift, okay, from point 1, okay, or the pull number 1, okay, shift to the point number 3, so we can see that it's actually radially moving away, right, from the origin. So if we draw a radial line, okay, connecting them, okay, and we shift along this line, so what happens is that when it moves along the radial line, we are maintaining the overshoot, right? So we will able to maintain the overshoot, but then because of the imaginary value now also increase, right? So these imaginary values increase will result to a faster frequency, okay? At the same time, when we shift it from point 1 to point 3, okay, the real part also increase. So when this one increase accordingly, then the so-called overshoot also increase according to that. So when this increase in the radial form, so in that way, okay, we can maintain the overshoot line, right? So this is how we can control, right? This is the idea of how we can visualize the performance, okay, by shifting all these pull, right? So the shifting of the pull, how it can be controlled and so on, we will cover that in the design part in the later sections, okay, or the later chapter, okay, when we try to analyze further, right? So this is the idea behind why we want to draw the S-plane, okay, and from the S-plane how this will shift and later part we will in the later few chapters we will start to analyze, okay, how this changes of the pool, okay, we can draw a locus of it, okay, and we can select accordingly uh, to meet our design requirement, right? Here is a quick analysis of a feedback system, okay. Remember previously what we deal with mainly on an open loop, right? So our examples previously is related to an open loop system, okay. For sure, since we also know that we can always simplify our systems, right? So when we deal with feedback systems, okay, our equations just slightly change, right? So that would not affect us much, right? So what we can see here, right, is if we have this feedback second order feedback system, okay, which have k divided by s bracket s plus a. So basically this, when we multiply it, we will get s squared plus as, right? So we don't have the constant part. So if this is the case, okay, when we draw a feedback loop, then we will obtain this, okay, exactly where we have add the k part, right? So from here we can actually see, we can transform this so-called feedback system into a very similar second order transfer function, similar to the one like in the open loop, right? Okay, so this is the way, okay, where later on we can always control, right, the equations by maybe adding a feedback, right? So by adding this one, okay, to these equations, we get this type of performance, okay. Then from there onwards you can also vary the k, right? By varying the k, then the pool we can now shift to different directions, okay, by controlling this value of k, right? Then we can actually detect the type of system that we would want to, and from there also we can select the type of performance that we want, right? So this is the idea behind it, right? And if we relate to these equations, okay, where we use k and a, right, instead of the damping ratio and the omega n, right? So from there, right, what we can see is that there is a point where we would reach critically damped critically damped performance, right? So we would see that that is when k is between 0 to a squared over 4, okay, we can always get this relationship, okay. When k is between this range, what happens is that it would remain over them, all right? So when the value is equals to this value, then it will become critically damped, right? Then when the value of k is more than this value, okay, the value is more than this value, the k value, the k we call it as gain, right? So that's why we say for the gain above this, okay. So from here onwards also you have to get familiar with the terms called gain, okay. Gain is just a multiplication or factors, all right? So this would be when you multiply it, okay, so we call that as a gain. So for the gain above a squared divided by 4, right? So then our system now become under damped, right? So by selecting a proper value for our gain later on, right? So we can actually control the performance. If the performance of the k is may not good enough, then we can actually add a controller, okay, to control the value of the k. This is where we would want to control and adjust the performance of our system, right? So this is the idea behind it, right? So again, this examples is straightforward, okay, just to illustrate how you can obtain all the related value, okay, even though when we see this familiar form of transfer functions, we can actually add a feedback loop, okay, unity feedback loop, okay, to convert it into this form. And from this form, then we would know that this would be the omega n square, and this would be omega n, the natural frequency, multiplied by the damping ratio. And from there onwards, you can actually predict the performance of it, right? So you can go through these examples on your own, right, in detail, okay, and this is the steps of it, right? So far, is there any questions before we proceed to the next sections? Okay, so if no questions, then we will proceed on the second chapter, okay, since we might be behind a bit, alright, from our original schedules because of the holiday, right? Okay, so next we would now want to see the steady state error, right? So as we know, we have a steady state value or the final value, okay, when we run systems, then it will reach to our final value, right? So the problem is whether this final value is what we want or not, alright? And that's why we try to measure the difference between the final value and our target value, okay, our original intended value that we give in, right? So this would try to address our course outcome number 3, okay, which is related to the steady state error of the control system, okay. Just an overview to give you an idea of how these things are actually now being implemented in so-called real life problem, okay. So all these equations basically can be in the form of mechanical devices, okay. It can be from a very basic gear, okay, a simple machine, motor control, okay, and to even the process control like these examples, okay, the heat exchanger process, okay. So just look at this heat exchanger process as an example to give you an idea of it, right? So the purpose of this heat exchanger is to maintain the temperature of the liquid, okay, to at a certain temperature, right? So we have a liquid going in, all right, and this liquid will be heated up to before it's being released, right, through a heat exchanger. So we have a very hot steam to actually heat it up, right? Now the problem is if we want to maintain the temperature, okay, before we supply to our process, okay, so we would want to measure the temperature over here, okay. So this temperature, since we want to control it, then we would want to like set a temperature, let's say 90 degrees Celsius, okay. So maybe the liquid comes in maybe in a room temperature 25 degree, when during winter, if it is a 4 seasons, okay, then this will drop to 3 degrees Celsius, 4 degrees Celsius, or during summer, then this will shoot up to maybe 35 degrees Celsius. So it depends, okay. So this will fluctuate, but what happens is that we intend to control what is the out, okay, what we don't care what is the in here, right? So in our system here, we can always represent this heat exchanger process into a simpler block diagram, where we would want to control the output, the temperature at this point, the TS, okay, the TT and the TS, right, by setting a desired temperature, right? So we would set a desired temperature over here. Okay, so let's say we are setting a desired temperature of 90 degrees. So we are actually giving a step input to it, okay. We tell the system, okay, I set 90 degrees, so the system will now at 0 second, it will now start to give 90-degree instructions, okay, to our process. Okay, so internally what happens is that they will keep comparing this 90-degree with the sensor, right? The performance of the sensor. So here the performance of the sensor might be in like, if it is a second order system, then we will get these fluctuations, or if it is a first order system, then we will get this performance, right? So the performance we don't know, right? So it depends on what we give in over here, right? But our intention is to control. What happens is that sometimes, okay, if we give a step input, okay, if we give a step input like this, okay, they might have a certain error, right? So this error may occurs, okay, regardless of how you change, right? So we would see that after it gets steady, there is a difference between our input 90 degree, or then the output may be 95 degree, okay? So there is always a steady state. We will call this as a steady state error, right? So this is where we would want to evaluate this kind of steady state error, whether the systems originally, when it is being designed, there is this kind of error or not, right? When we give this kind of input. So that is where it is important for us to, where during the design of a system, we would want to know whether there is this kind of error or not, right? So this is our questions to be addressed in this sections, okay? Then also beside of this, okay, we will also want the system to be stable, okay? But we will do this in the next chapter, okay, talking about how we evaluate whether the system is stable or not, okay? And this stability would result like this will continue to grow, okay? If the value continue to grow, okay, out of control, then we say the system is unstable, right? And we don't want that kind of system, okay, at the first place, okay? If the system is unstable, then no point we are actually measuring the error, right? But if the system is stable, then we would want to know, okay, whether the existing system, there is so-called preset type of error exists in the design or not, right? So this is the point, right? So in the following sections, okay, we will assume that the system that we present or we try to analyze on the steady state error are stable, okay? The system are stable at the first place, right? So assume everything is stable, then you will get a steady state error, right? So here is the definitions of steady state error. So it basically just the difference between the input and the output, right? So you want to compare the input and the output. So you will have input, okay, the blue line, okay, as our desire, and the output, the time response, okay, how it would behave, okay, after we set the value of 90 degrees Celsius, okay? So it will now shoot up and then stabilize, right? So this is a steady state value, and from there we can see an error. So this difference will be captured when the time is long enough, right? Assuming everything is stable, it's already past the steady state or the settling time, right? So since we want to analyze for all cases, okay, we would just take time equals or approach infinity, okay, for very long until it change, right? So here we would usually give three type of test input. Again, I've mentioned this previously. These three signal or waveform are important, or basic waveform, okay, that actually control the response of our system, right? If we just set a value, then this value we can say as a step input, okay? So if a step input, then the time function will be 1, okay? and the Laplace transform will 1 over s. Okay, if we are giving a ramp input, okay, constantly increase, then the time function will be according to time t, and the Laplace transform will be 1 over s squared. Okay, similar to the parabola, then this would be increase exponentially, right? So the time function will be 1 over t squared, and the Laplace transform will be 1 over s cubed, right? So the physical interpretations between them is that if we are assuming this is a position control, so we are mentioning this as a position. Let's say this is a positions, right? Okay, so this is a positions, right? So let's say this is a positions control, right? So positions. So if these three graph or curve are representing a positions control, meaning to say when we give a step input, okay, we would want it to maintain a new positions, okay, over a certain time. Okay, so we would interpret that as a constant positions, okay, after a shift. But if we are giving a ramp input, meaning to say we want the object, okay, or the point or the particles actually change at a constant velocity, right? So the position will change, okay, as time progress, right? Whereas in these interpretations, the positions actually change, okay, or the distance change, okay, in the exponential way, right? And that represent a constant accelerations. Okay, that is the physical relationship between the type of input and the behavior of it, right? So this physical interpretation may be related to the motor positioning, right? So whether you want to just rotate and stop, okay, or you want it to continuously rotate, okay, by giving a signal of constant velocity, or you want to give a signal of constant acceleration. So that is how we would give different type of waveform as an input, right? So this is the idea behind it. Okay, so this is the descriptions of what I've mentioned previously. Now we also want to address the source of the steady state error so far. Okay, so the source of the steady state error actually mainly come from different sources. Okay, it can be due to the non-linearity of the system or the source, okay, like backlash in the gears, motors, and so on, right? But then for this course, okay, we would not looking beyond the non-linear side. Okay, we just want to give you a fundamentals idea of how to control and so-called ideal system, okay, with the injections of maybe a disturbance and so on later on, right? So for this course purpose, okay, we just concern only on the error that arise or due to the configurations of the system, okay, meaning to say the transfer functions, how they are arranged parallel or series and so on, right? As well as the type of input. Okay, so whether you want to use step input, ramp, or parabolas type of input. So we just concentrate on these two things. Okay, the rest we will not take care at this course, right? So now since we already have a predefined so-called predefined system or the configurations, okay, then also we have a type of input that we have, right? We know the type of input that we want to inject to our system. Okay, so then from there, now we would want to know, okay, how actually all these changes, okay, the type of input and the system, okay, the whether first order, second order, whatever it is, or feedback loop, so how they would actually change or affect the steady state error, right? But so again, we just a reminder, okay, this steady state actually is corresponding to the oscillation part, right? The natural frequency part, remember, right, in our whole equations, okay? So this represent the natural frequency response approaching zero when time approach infinity, meaning long enough for the natural frequency to damp out and become zero, right? So this is the idea of it, okay? If the natural frequency doesn't damp out over time, it keep increasing, then the system is no longer stable, right? So if it is not stable, then it's actually not controllable, and we don't want this kind of system, okay? We always want to take control of the system, right? So first we must check for the stability before we perform this steady state error analysis as well as design, okay? So now if you look at the slides here, they are actually slightly different from the one I have uploaded in the Google Classroom, okay? Just a bit updated, but the content remain the same, okay? Only the figures I just maybe redraw it here and there and resizing, so no worry on that, right? Okay, so on the evaluations of the steady state error, now we can see that if we are giving a step input, okay, now remember here we would now to evaluate the changes of the input, okay? So if we are giving a step input over here, so there will only two possible outcome, whether you get a zero steady state error, okay, which the output 1 as shown as output 1, or there is a value, okay, which a finite steady state error, okay, which is represented by output number 2, right? So this is one way of it, okay? Then when we give a different type of input, let's say now in this case we give a ramp input, then in the ramp input we would have three type of possible output now, okay? Whether the first output may reach the zero steady state error, right? So this is our input, then this output now go up and then reach and maintain at the steady state that give us zero error, or the second type of output which always a finite steady state error, right, the output number 2, and the third one, okay, this error actually increase, okay, as time increase, so this error will become like infinity over time, right? So output number 3 occurs when the slope actually differ, right? So it may in this case go down, or maybe this one goes up like this, so the steady state error now change, okay, or continuously increase, okay, when time become infinity, okay, or long enough, right? So now what is the relationship between the type of system and the type of steady state error? This is our main question that we intend to address, okay, next, right? Look at this closed loop control, okay? As we say, the error is the difference between the input and the output, the input and the output, right? So if we want to compare them, right, so we can represent either using this form or like in the feedback loop form, okay? Either way will be good, right? So we can see that if we want to compare, so we will just do use a comparator, minus them out, right? So input minus the output, right? So minus the output, which gives us the error, right? Same with this, okay? In the feedback loop, the output goes back, okay, and we compare the input and the output, give us the error, right? So both representations of control would be okay, right? And then we will see how they actually change according to the type of input and the type of input, okay, on the in order for us to get the steady state error, right? Okay, so in the system, okay, so in the system now, okay, we have this so-called closed loop, right? So we start with this closed loop, right? So in the system, we may have the input, the output, and the error, right? When we consider a step input, okay, when we consider a step input, what happens is that in the steady state, when the output reach a steady state, if the output is equals to the input, then the error is 0, right? It's very straightforward. However, if the output and the input have a difference or a fixed value, okay, then there will be a finite steady state error. Remember, when we give a step input, there is only two possible outcomes, whether 0 steady state error or a finite steady state error, right? So this is the case, okay? So you will either have a 0 steady state error or there is a value or a finite steady state error, okay? And this steady state error, okay, are mainly because of the gain, okay, of the gain here, the k value over here, right? Because of this k, okay, whatever we give in, let's say this k is not 1, let's say this k is 10, right? So if we give 1, this 1 multiplied by 10 gain 10, so the output will be 10, right? So when 10 compared to 1, then the difference is 9, then 9 multiplied by k. So there is always this kind of gain, okay, where as the system progress, right? So virtually because of this gain, the error will exist, all right? The error will exist whether it becomes 0 or non-zero. That is the problem, right? So if we try to represent them in equations, then for sure we would want to say that the output during steady state, okay, since we are talking about the steady state error, so all these values are when the system have reached a steady state. So this steady state output, okay, we call C steady state, okay, and the error during the steady state, the E steady state, okay, then through this system, the output would be the gain multiplied by our error steady state, right? E steady state. So if we rearrange this one, we bring it over, then we will get these equations, right? So error during steady state equals to 1 over k of our steady state output, okay? Meaning to say here, 1 over k, if we continuously increase the gain, the k value, then this error, we intend to control the error. So this error now will become smaller and smaller and smaller, and at one time you can say it is negligible. So meaning to say, by increasing the gain, okay, by increasing the k value, actually we can minimize the steady state error, right? So conclusions, we can say that the forward path, okay, always give us a steady state error, but this error would become negligible, diminish, okay, when the gain value increase, right? So this is the main idea behind it, okay, of using the gain, the k value, okay, to control the steady state error, right? Okay, remember we are still dealing with a step input, right? So this is when our input is a step input, right? So take into the account. Okay, always remember that. Now we are talking about step input, right? Since there is always a finite steady state error, okay, for step input when we apply a gain type of transfer functions, what we can do now, if we replace it with an integrator, okay, integrator means the function is all a gain divided by s, okay, so this is in a type of integrator functions, okay, in our transfer functions. So what happens is that when we change this to an integrator type, okay, then there will be a zero error steady state. Okay, previously, because of using gain, there is always a finite steady state error, right? But here, by using integrator, we will get a zero steady state error, right, when we apply a step input. Okay, so here, as the output response, okay, the CT increase, okay, then the error actually decrease, sorry, okay, it decrease because of these features, right? So when CT continuously add up, okay, then the error actually continuously going down until it becomes zero because of this integrator. Okay, we are not minus it directly, but then we do an integrator or integrations, okay, so that these changes actually become smaller and smaller. It's not a fixed multiplications anymore, right? So therefore this decrease will continue until a zero error, and that is where this integrator will give us so-called zero value, I would say, because of the changes of the transfer functions, okay, as this error becomes smaller and smaller, this value actually change, okay, or affect the output by minimizing the effect of it, okay, and eventually becomes zero. Okay, this term will become zero at the end, okay, when the error is zero. Okay, then this will multiply by a zero, so eventually no error will exist, okay, at the end, right? So this is the idea of adding an integrator, right? Then if we look the steady state error from another perspective, okay, from this perspective, okay, we call it as a TS terms itself. Okay, previously we can see that this is in this way, okay, in the feedback, so-called feedback loop type, right? So if we look at another just configurations of it, right? So how, if we try to express in the other way, then we want to see how actually they actually change, right, according to different part of the parameter. This we want to relate the error, okay, the E, with respect to the transfer function T here, right? So if we take into this, okay, we just use the basic constructions of it, okay, the error is equals to the R minus the CS, okay, and we also know that the CS is R multiplied by T, right? Okay, so substitute in, then we can get this equation, okay, which is related, the error is related to the input signal, okay, the R multiplied by 1 minus TS, okay, 1 minus TS, okay, so this is the equations that we will deal with, okay, later on. Okay, so based on that equations, now we would apply a theorem, we call it as final value theorem. Okay, so this theorem basically is a mathematical theorem, right, where we intend to evaluate the final value when time approaches infinity, all right, and because of the Laplace transform behavior itself, okay, when the time approach infinity, okay, when the time approach infinity, the Laplace form, okay, the s actually approach 0, okay, so we can always take a limit of it, okay. As our final value theorem, we will say that by taking limit when time approach infinity, okay, then we will know what is the error, okay, when time approach infinity, and we take the Laplace transform form, then this would be when s approach 0, okay. This, when we take the Laplace form as well, we would multiply by an s at the front, okay, so we have s e s, right. So this is the equation that we will deal with to evaluate the final or the steady state error, right. Now we replace the e value into our equations, okay. This is our basic equations, okay, the final value theorem equations over here. So when we replace the e value over here, okay, remember the input multiply by 1 minus the t, the transfer functions, okay. So we will now immediately obtain the so-called steady state error, and you will notice that we don't need even to plot the graph or solve the Laplace transform, okay. So by doing this, okay, we skip all the steps, we immediately get the steady state error, okay. This is the idea behind it, right. So just look at an examples, okay. For these systems, try to find the steady state error if given that the transfer function is as such, okay, and we are applying a unit step input, right. So here is the block diagram, right. Here is the block diagram, and we just have to replace them into the equations, right. We know that if the system is stable, then we can apply this final value theorem, right. And when we apply this, we would now see that we just put it in, right. So the input for unit step is 1 over s, okay, so we can cancel out 1 s and 1 over s cancel out, remain is 1 minus ts, right. So this 1 minus ts is basically this one, right. Okay, so we just put it in, right, assuming we have already do our task, okay, to find the error, okay, just substitute into each other, right. So now to evaluate this steady state error, okay, what we would do now is that when s approaches 0, meaning to say we assume s is 0 now, okay, so s cancel out, okay, so these two cancel out, now become s square, okay. So if s is 0, so this term 0, this term 0, this term 0, this term 0, remain is 5 over 10, right, meaning to say our steady state error would be 5 over 10, which is 1 over 2, right. So by looking at the equation, the type of input, using a final value theorem, we can know what is the steady state error, okay. So this is how we can apply it. Then also beside using this form, okay, beside using this form, okay, this form of error, then we can also use another form of error, okay, when we are subjected to unity feedback, right. So in this form, we would just slightly rearrange our equations, okay. Again, very similar, r, then we have c, okay, the error is between r minus cs, right, and we know that cs is e multiplied by g, okay. Just since this is a unity feedback, right, then we know that it would be the R, okay, the R itself, okay, divided by 1 plus GS, okay. So this is our error equations, okay, at the end after we substitute into them and solve them, right. So you can see that this error equations now is in terms of R and G, right. So this G is similar to the previous one. Previous one we used T, but the T previous one is like in the open loop form, okay, whereas in this form is in the closed loop form, right. Remember, just to re-highlight, right. So assuming we don't draw this one, okay, you can see that this is a open loop, everything direct, we just want to know the difference between them, okay. Whereas in this form, the expression is that we will take this input going back and re-enter it into our system, right. So our error equation just slightly change, okay, to R divided by 1 plus GS, okay. And because of this change, okay, we again use the final value theorem, which is taking limit when s approach 0 with s multiplied by es, okay. So we have s multiplied by this es over here, okay, we substitute, then this is our final value theorem for this so-called closed loop unity feedback system, right. So that is the slight changes between them, right. So now if we are putting a step input to our closed loop system, okay, then we would get this form, right, because we know we put 1 over s to the RS position, so when we cancel out, this become 1, right. So when this become 1, this limit now we can also distribute into each of these, okay. So right, so when we distribute into each of these, then it's basically taking the limit when s approaches 0 for the transfer function g, right. And these transfer functions would be the gain forward, okay, the value that we have in the transfer functions, okay. So now because of these constructions, now if we would desire a zero steady state error, if we want this to have a zero steady state, then we want this to become 0, or we would want this to become as big as possible, so that this whole term becomes 0, right. So in order for that, this is where we want this term, okay, only this term, right, reaching or it become infinity, right. So by taking this equals to infinity, then we would get a 0 steady state error, right. So now how we would able to control this is that we can always break this transfer function into multiple partial fractions, okay. So we have this form, okay, let's say in this form, right. So we have multiple zeros and poles and so on, right. So there is also when the pole is at the origin, then we have this s, okay. It can be in the order of 1 or higher, right. So we may generally have this form of transfer functions, alright. So in order for us to have this 0 steady state error, what we need is that we need at least one pole, okay, this pole, okay, to be at the origin, right. So this pole will have an origin at 0, right, whereas the others we have pole at other finite positions, okay. So our interest would be at this part, okay. The rest we are not interested with actually, right? So the interested part would be this s power n, right? For us to get a zero steady state error, the n must be at least 1, okay, for this, okay, and that would satisfy our conditions, okay, to get a zero steady state error when a step input is given to the system, right? We call this s itself as an integrator, a pure integrator, right? So if you recall back the previous equations, okay, remember when we put an integrator, the k over s as our transfer functions, we would get a zero steady state error, okay, and this is why, okay, if we get at least one pure integrator, then we would get a zero steady state error, right? What if there is no integrator? Okay, so if no integrator, you will expect that you just have a gain k, right, like in the previous one, then the n is equals to 0, okay. So when k equals to when n equals to 0, okay, when n equals to 0, this term is not there, right? When we take limit s approach 0, okay, this one becomes 0, becomes 0, becomes 0, becomes 0, and becomes 0. So eventually we will get z1 multiplied by z2 divided by p1 multiplied by p2 and so on, and that results to a finite value, right? So you will get a finite value at the end, and that causes a finite error, okay, a certain error, okay, at the end instead of 0, right? So in summary, step input to this type of unity feedback system, the error will be only become 0 if there is at least one integrator in our forward path, okay, in our transfer functions, right? Next, we would want to see how other type of input actually affect the steady state error, right? Now if we try to put a ramp input into the unity feedback form, okay, unity feedback form, then again you will see that this rs now become 1 over s squared, okay, and because of that change, these terms will now become purely depends on 1 over limit s g, right? And again, if we want a zero steady state error, we want this denominator become as large as possible to become infinity, right? And for this to be satisfied, now because this have an s at the front, okay, we have an s at the front, right? So because of that, what happened is we need at least n equals 2 now, okay, because this s will be cancelled out, will cancelling out this, okay, if it is 1, right? So we need at least 2, okay, in the forward path, okay, in order for us to get a steady state error, okay, when our input is a ramp input, okay. So similar to the previous case, okay, if there is only one integrators, okay, or integrations, then you will cancel out and you will get a finite value, right? Now when we apply integrator, okay, to our ramp input, okay, we would get either finite or zero steady state. If we are giving a ramp input and our transfer functions doesn't contain any integrator. Okay, if we don't have any integrator in our forward path, then the problem will now, when we take limit of the SG, we will get 0. Okay, and when this becomes 0 instead of a finite value, when we put it back to our equation, when this becomes 0, 1 over 0, then our error now will become infinity. Okay, and this is where the error continuously increase or diverging from the system, okay, or the steady state value. So by looking at this type of input, okay, the type of input that we intend to put in, okay, then we would now immediately when we do the design, we will immediately come into mind, okay, which type of system we must implement, okay, in order to cater with all this steady state error. Okay, similar to the parabola, okay, and the RAM, okay, is very straightforward. Now onwards, okay, we just change the input into 1 over s cubed, okay, because of the s cubed, then these terms become s squared, and because of this, then our integrator now must at least 3, okay, in our forward, in order for us to get a zero steady state error. Okay, if it is less than 3, okay, only 2, then you will get a finite error. If it get dropped further, become 1 or less, then you will get an infinite, right? More is okay, less, then you have this type of undesirable steady state error, right? So here is a straightforward examples, okay, that you can try it. All right, so this is a unity unity feedback system. Okay, so the transfer functions here we would see as with one integrator, right, and one gain value k, right, the rest is 0 and post form, right? So based on this, actually we can now see that because of one integrator, if we could give a step input, then we get 0 steady state error. Okay, if we give a RAM, then this will give us a finite, and so on, right? So you just try to input different type of input. Okay, so this is 5 UT means a step input of 5. Okay, then 5T, T represent a RAM, right? So 5T, okay, is a RAM input with a multiplication of 5. Okay, then this is a parabola input. All right, so immediately you can evaluate the type of the finite or the steady state error. Okay, as we say, for a step input, okay, we will get 0. Okay, for a RAM input, we will get a finite value, and when we change the type of input to the parabola input, then our error now become infinity, right? So this is the way of doing it, right? So far, any questions before we proceed? Okay, we would try to use a term, okay, where everyone would able to understand easier. Okay, so you will actually see all these terms exist somewhere. Okay, maybe when you are looking for specifications of a system, then they may give you this kind of a static error constant. Okay, just a terms that everyone may use, right? So what is this term is all about is trying to describe the performance of the steady state error, right? That if we have, remember this is our steady state error equations, right? So what is the static error constant is that we are giving this part, okay, this denominator, the relevant denominators, okay, as a constant. Okay, so since this first one, okay, is dealing with the step input, okay, that would give us a step input, so-called zero or finite steady state error, okay, then we would say that this is the position constant or the Kp, right? When we add an s at the front, okay, so when we add an s to the front, so this would be related to the RAM input, right? That would give us a zero or a static, a zero or a finite steady state error. So we will call this as a velocity constant. Okay, similarly, when we have s squared, then that would be an acceleration constant, Ka, okay, position, velocity, accelerations. Okay, so this is just a terms that we would use, okay, three terms that we use in the denominators, okay, to identify or to estimate the steady state error. Okay, so what we can see in this type of steady state error is that when the constant, when we say error constant, static error constant instead of steady state error, so if we want to decrease the steady state error, we want to increase this constant, okay, increase, okay, the higher the better. If we get this constant as infinity, let's say we get the Ka as infinity, meaning to say if we are giving a parabola as input, we would get a zero steady state error. Okay, if we get Kv as infinity, okay, meaning to say if we are giving the velocity type of input, then the steady state error will be zero, right? So this is how they are related. Okay, here is an examples, okay, to evaluate the static error constant, okay, and find what is the expected error outcome, right? So very straightforward, right? You just have to put it in, calculate the constant itself, right? Then since this is a finite value, so if finite value, then we would get the steady state error as 1 over Kp, right? Remember 1 over plus 1 plus Kp. For RAM input 1 over Kv, and for parabola 1 over Ka. Okay, so you will get infinity. Okay, whereas for this one, since we can't get infinity, then there is a static or finite, there will be a finite steady state error. Okay, so here is another few examples that you can go through on your own, right? Just change of the equations or the transfer function within this, right? So this is the effect of the input itself. Next, we will want to classify our steady state error according to, we call it system type, all right? We need to say our transfer function itself, right? We can know that input will affect, the transfer function also will affect, right, the steady state error. So here let's again focus on the unity feedback system. Okay, typical feedback system that we have. Right now, we know the static error constant, and we also know this what we call the transfer functions. Okay, so these transfer functions will play a important role, okay, to determine what type of static error, okay, that we want, okay, or the steady state error that we want. So here we will give the name of the system depending on the integration that we have, okay, because this play the more important role, okay, in determining the type of response that you get. Okay, so here the integrator is important, right? So we give the name according to the number of integrator. So if the number of integrator, if when n equals to 1, then we will call that is system type 1. When n equals to 2, then we say that as system type 2, and so on, right? So we are giving the numbering, okay, for it. When the n is equals to 0, we will say that would be a type 0 system, okay. And because of that, now we can summarize the whole idea is that when there is no integrator, when a step input is given, then we would get a constant steady state error, okay. When we increase the system type, okay, without increasing the step or the input, the order of the input itself, then now it will become infinity as the system type increase, right? But then if but when we actually change to, I would say, type 1, okay, when the input is a RAM input, alright, so therefore from here we would now see that for type 0 we would get the static error constant equals to 0, and this will cause our error to become infinity, right? So you will see that there is this so-called boundary, right, where when the system type increase, okay, the input should also so-called increase accordingly, or in vice versa way, okay. When the type of input, the order increase, then our system type should also increase to cater so that we will not have to deal with the infinite error over here, right? So this is the relationship between the input and the system type, right? Okay. So again, you can always try this at home, right, just to evaluate what is the KP, KA, and KB, and from there onwards you can actually interpret what type of system or the steady state error, okay, corresponding to different type of input, right? So here is the steps, okay, that you may go through, right? The next one would be, we call it as specifications, okay. In these specifications, the steady state constants are actually used to specify the steady state error characteristic. That's why I've mentioned previously, in some control system, they will actually write KA, KV, KP for you, okay, in some particular system, and that actually tells you what is the specifications of that particular system, okay, that you have to deal with or you have bought in, right? So this is the specifications of your system itself, right? So here is an example. So if you have a control system with kV equals to 1000, okay, if we have kV equals to 1000, what does it mean is that the system is first stable, then second one is, since we are getting a value, okay, this is a value, so-called finite value, okay, a constant value for kV. So kV will only become finite when the system type is type 1, right? So go back again, okay, you can see that this constant value will only corresponding to different type of system type, okay, when the input change, right? And obviously this kV is only become constant when we are dealing with type 1 system. So immediately we know that the control system itself is a type 1 system, okay, even though the company or the manufacturer may not give you the transfer functions, okay. When they give you kV equals to a finite, then meaning to say we know that that is a type 1 system. So when it is a type 1 system, if we are giving a RAM input, then yes, we will get a so-called a finite constant, okay. But if we are giving a step input, then you will get a zero steady state error, okay. So this is how we can use this so-called specifications of steady state, it's the static error, okay, to helps you to select according to what you need, right? And also from this we can also conclude that the steady state error between the input RAM and the output RAM is 1 over kV, okay, because it gives us a slope of it, right? So this is how you can interpret them, right? Okay, based on that, now what if Kp equals to 1000, okay? What you can do is you can do the same thing again. You just put it in Kp equals to interpret, so you know that system is stable. This is Kp, then it's related to type 0, right? So since it's type 0, then the test signal would be step, okay. We are testing with Kp, so test signal will be step, and when the step input is given, then our steady state error will be 1 over 1 plus Kp, okay, refer to the previous equation, and our error will be 1 over 1001, right? So this is how you can interpret, right? Same thing for these examples, right? So you can try that on your own. Okay, so after going through the steady state for a unity feedback system, okay, now we would go through the steady state error for when we have our system is subjected to disturbance, okay. So this disturbance type of signal, okay, being implemented or injected between the controller and the plants are very similar to what's you have gone through previously in chapter 2C on the block diagram, right? Simplification of block diagram, okay. So we would want to analyze the effect of the disturbance, okay, by taking it part by part, okay. First we will take the disturbance side, okay, then we will consider the input as well, okay, and we superimpose the effect, okay, towards the output, right? So therefore in order to study the steady state error for disturbance, what we would do now, we express the steady state error, okay, with the disturbance being included here, right? So here as we can see, the output itself, okay, is basically the summations of two signal, okay. First one would be from the input, okay. So this input going through, okay, which being minus with the signal from the feedback. Okay, so we have this error. Okay, so this error signal, when we multiply by G1 and G2, we produce the output. Okay, so this being represented by these terms. Okay, whereas the disturbance itself, when it be injected in between the controller and the plant, okay, then they will be multiplied by this G2 itself, okay, and contribute to the output. So we have a G2. Okay, so the total output would be the summations of these two effects. Next, also we know that the error signal is basically the summations of the input signal as well as the output. Okay, so we will have the R minus the C, okay, that give us the the error signal. Okay, so from this, since we already know the output signal, okay, the CS, okay, therefore we just substitute into our equations, okay, rearrange our equations, and eventually we will get the error signal in terms of the input signal, okay, as well as the disturbance signal. Okay, so we can actually explicitly separate them into these two terms. Okay, so now based on these two terms, okay, what we can do in order to get the steady state error, again we will take the time towards the infinity, and in that sense, using the final value theorem, therefore the s should approach 0, okay, by taking the limit when s is approaching 0, okay, so we have the limit SE, okay, given as such. Okay, so we will put the whole error terms or error equations into our final value theorem. Okay, and from this we can actually see that again it is summations of the steady state error due to the input as well as the steady state error due to the disturbance, right? So we can break them into these two separate terms, right? So now considering a step disturbance, okay, so when we take the step disturbance, so we would put the ds equals to 1 over s, okay, and because of this is a step disturbance, therefore we just put into these terms, okay, this particular terms over here, 1 over s, okay, therefore we eventually will get this error, steady state error component, okay, due to the step disturbance given by minus 1 over limit 1 over g2 plus limit g1, right? So here we can see that because this is 1 over the denominator, okay, so whenever we want to decrease the error, okay, we would want to increase the value of the denominator, okay, therefore if we can increase the value or the gain of g1, okay, then they would eventually reduce the steady state error produced by this step disturbance. Okay, similarly on this term itself, okay, since this is inversely proportional, therefore by decreasing the gain of the g2, then we would able to reduce the effect of the step disturbance. Okay, so how would this being possible? Okay, we can again analyze it through the separations of the disturbance from the input. Okay, assuming the input is 0, okay, we only consider the disturbance itself. Okay, therefore when we rearrange this block diagram, we can see that this disturbance is similar to an input. Okay, then this is our plant where the controller is similar to the feedback gain, right? So from this block diagram itself, it is very direct that the disturbance, okay, when you go through a plant, okay, it will produce the output. So if we can reduce the gain of the plant, then the disturbance effect will be reduced. Okay, whereas if because of the feedback side of the G1, okay, therefore if we can increase this G1, therefore we can somehow suppress or dilutes the effect of the disturbance towards the output. Okay, so this is why there is this effect of G1 and G2, okay, on the disturbance itself. Okay. So next, we would also go through the steady state error for a non-unity feedback system. Okay, so here, as we have seen previously, we only consider the unity feedback system, okay, steady state error for a unity feedback system. So how we can convert this into a non-unity feedback system is that we would want to again reduce our block diagram into a familiar unity feedback system. Okay, so this non-unity feedback system usually present because we want to improve the performance of our on control system. So what we can do is we introduce this feedback system over here, and because of this feedback system is no longer directly connected between the output and the input, therefore we would make these terms as an actuating signal instead of an error signal. Okay, therefore now again we also, since they do some kind of multiplications, okay, through a factors, okay, at the feedback side, okay, therefore we would also want we would assume, okay, that the unit for these two input and outputs, okay, by the C going back, okay, should have the same unit, okay, so that they can actually cancel out each other at the end, right? But nevertheless, the error signal or the steady state error signal would be given by the E equals to R minus C, okay, very similar to the previous unity feedback system. Okay, so our intention here is to convert this non-unity feedback system into a unity feedback system. How we can do that is we will introduce two additional feedback, okay, one with the gain of -1 and another one would be with a gain of 1. Okay, so when we total this together, eventually we do not change the behavior of our non-unity control system, right? So here, based on this, therefore what we want is we want to retain this unity feedback, okay, while the remaining we would want to combine them together. Okay, so how to combine this together? So we would first take these two, okay, we can add them up because they are in the parallel form. Okay, so we add them up to get a h minus 1. Okay, so once we have this h minus 1 and the g itself, we would also see that this is again a familiar form of a feedback system, okay, where we can simplify this into a feed-forward transfer functions given by g divided by 1, since this is minus, so this would be plus g and multiplied by h minus 1. Okay, so g multiplied by h minus 1, so you will get 1 plus gh minus g. Okay, so eventually we can simplify our, or we can convert our non-unity feedback system into a unity feedback system with a feed-forward transfer function of g over 1 plus gh minus g. Right? So based on that conversions, therefore we can approach this kind of questions easily, right, by converting them to the similar form of unity feedback system. Okay, so take these examples where we have a system of a feed-forward transfer functions and the feedback transfer functions given as such. Okay, so what we can do is we convert them into equivalent transfer functions by taking the g over 1 plus gh minus g. All right, so this would be our g and this would be our h. So taking that, we can see that the g itself is 10 over s multiplied by s plus 10s, right? Okay, so we will just write it down. Then for the h itself, okay, so g we would put it there, right? Then the h itself we would multiply, okay, then minus. So eventually when we do the operations, we will get this equivalent transfer feed-forward transfer functions, okay, given by 10 multiplied by s plus 5 divided by s power 3 plus 15s square minus 50s minus 400, right? So from this equivalent transfer functions, when we try to analyze it, then we will see that we cannot actually factorize any s term out, okay, meaning to say this system have a type 0 system, okay. So if it is a type 0 system, then what we can do is we would know that the appropriate static error constant would be a position constant kp, right? That would yield a finite steady state error, okay. So we just apply a kp in this case since it's a type 0 system, okay. So we would use a kp. So based on that, again we will use the final value theorem, okay, which we take the s approaching 0. So this would be 0 0 0 0. So it's 500 divided by minus 400, okay. So we will get a steady state position constant, error constant would be minus 5 over 4, okay. And the corresponding steady state error would be when we apply into our equations, we would get minus 4, okay. So since this is minus 4, okay, whenever we see an error, okay, which have a minus sign, meaning to say, remember the signal itself is that there is a feedback from the output and we are comparing it with the input, okay. So input is plus, the feedback is minus. So if we get the summations become negative, okay, therefore meaning to say the signal from the output is greater than the signal from the input, okay. So this is how we can interpret the steady state error, okay, given by this negative form. All right, so the last sections for this steady state error sections would be the sensitivity, okay. So we also want to know, beside the steady state error, we want to know how sensitive it is, okay, towards any change of the parameter, okay. For example, the k constant, or maybe you have a and other parameter, okay, how sensitive they are towards any changes of this, okay. So sensitivity refers to the degree to which the system parameters change, okay, or affect the system transfer functions, okay. So if we know how sensitive it is, therefore we could also know how would it perform, okay, based on the changes of the parameter itself, right? So which parameter is more dominant and so on, right? So this is how we use this kind of information for our design knowledge at the later stage, right? The sensitivity in terms of control, we would define that as the ratio of the fractions change in the function, okay, in the function itself. So we will put f, okay, compare it to the fraction change in the parameter p, okay. So we would use functions to parameter, okay, f to p, right? And we again for this sensitivity, we will take the fractional change of the parameter trying to approach 0, okay. So we will put p approaching 0. So therefore the sensitivity equations, when we use f to p, okay, it would be equals to the limit p approaching 0 when delta f over f, okay, so this is a fractional change of the functions, divide by delta p divide p. This is a fractional change of the parameter itself, okay. So this is function, then, and this is the parameter, right? So eventually when we simplify this, then we will get a p divided by f multiplied by the partial derivative of a functions respect to the parameter terms, okay, p. Okay, so how we would visualize this, okay. So just a simple idea first, right? So let's assume a functions of f, okay, equals to k divided by k plus a. Assuming we don't change the k, we only want to know how the a actually affect this function. So we change the a. So from 100, when we change to 300, we are actually changing 200% of the a parameter, okay. And we realize that the f actually decrease, okay, by minus 65%, okay. So this is how we can actually see the sensitivity in terms of changing the a and how it would affect the functions f, okay. And since this is less than 100%, okay, less than 100%, therefore we can actually see that, and also it's shrinking, okay, in the negative side. We will say that this is a reduced sensitivity, okay. So in order to use this equation, we will see another examples, okay. So this examples is how we would check, okay, the sensitivity of the steady state error, okay. So now the functions that we are referring to, okay, previously we say this f, right? So now the functions would be our steady state error, okay. So we want to check the sensitivity of this steady state error functions when the parameter k and parameter a in this system change, okay, how it would actually affect the steady state error, right? So assuming again this system is subjected to a step input, okay, so we will put 1 over s over here, and when we deal with a step input, okay, therefore again we have to analyze our system type. So here again, very obvious, our system type would be type 0, since we don't have a s terms at the front, okay. So this is a type 0 system, and when it is subjected to a step input, type 0 system itself will yield a steady state error with a finite value, okay. And that finite value can be given as we just use the previous final value theorem, okay, and to calculate, right? Then we will yield that the steady state error would be AB divided by AB plus K, okay, since this equal near to zero, okay. So it's K over A multiplied by B, right? So put it in, then apply to our final value theorem, then we will get AB divided by AB plus K, right? So now this is our functions, okay. Remember, to get the sensitivity, we are looking for the functions fractional change divided by the fractional change in the parameter itself, alright. So now once we have that, okay, we use the equations of the sensitivity. So we would take the functions of error and the parameter of a first, okay. So we will see how it changed to a, then later we will see how it changed to k, right? So we take the a side, okay, so therefore we will get the equations of a over e multiplied by the partial derivative of e respect to the parameter a, okay. So we just rewrite this a over e is given by these terms, okay. We just put it here, okay. Then we take the partial derivative of these equations, okay, respect to a, okay, meaning to say when we take with respect to a, then these terms, this partial fractions terms, okay, can be calculated as such, right? So it would be the bottom side, okay, so ab plus k, okay, multiplied by the upper side, okay, after we differentiate the a, okay, so we have b here minus the ab square divided by the bottom side, okay, with a square, okay. So eventually when we solve it, then we get this term, right? So how you do the differentiations, okay, so you can just refer back to the chain rules, okay, how you can do this, okay. So similar to the sensitivity of the steady state error due to the change in parameter k, you just use k over e multiplied by the partial derivative of e over dk, right? So you will get minus k over ab plus k. So from this value itself, okay, what we will notice that is that if a and b is positive, okay, when this two value is positive, then for this fraction itself will always be less than 1, okay, because k value, let's say k value is 100 divided by 100 plus a positive value, so therefore this would be less than 1, okay, if ab is positive. Same thing for this, okay, it will be less than 1, okay, when ab is positive, right? So therefore because of that, the feedback in this case would give us a reduced sensitivity, okay. The effect would be reduced instead of increased when we change the AB terms, right? So how far or how much they change, it depends on the parameter. Since both are from these equations are very similar equations, only one is plus, one is minus, therefore the effect would be similar, but we will know that it gives us a reduced sensitivity to the variations of both parameter a and k, okay. So that concludes this part of the steady state error, right? Thank you. After rechecking the slides, then I realized the announcement made in week 7 there is some mistake with the dates, okay. I mixed it up with the another course, right? So just a corrections to that, okay. So as we can see, we are now at the SEM break, right? So here is the SEM break, okay. Then you have taken the test on few days back, right? So therefore from that onward, what we can see is that we will have chapter 5, chapter 6 AB and 7 AB to cover. So hopefully by the week 14 we would able to finish everything. We can cover everything before you come to a study week, okay. And because of some circumstance, okay, so for this course we would do it with tests as well as a final exam, right? So don't worry about the final exam, it would be conducted online. Very likely is online due to the MCO, right? CMCO. So what you would do is that it's very similar to our online test, okay. The only difference is that it will be conducted at a prescribed time according to the BPA schedule, okay. That's all, right? So the submissions and the instructions would be given in the smart 3 if not mistaken, okay. But never mind, okay. At the end, maybe when the time getting closer, okay, we will have a clear instructions on how we would conduct the final exams through the BPA smart 3, right? So just our planning. So we have conducted the test 1 here, okay. Then after that we will have this test 2. So tentatively we would want to have this test 2 at 7th of January 2021, okay. That would cover from this particular chapter 4 until chapter 6A, Okay, 6A. So hopefully by before Christmas, then we would able to cover 6A. Then you will have 1 week. Okay, yeah, 1 week more than that. Okay, then we will have the test, right? So this is our current planning. Okay, so hope that would be clear and fine with you.